Welcome to the last part in the time series course. Today, we will continue with co-integration analysis, but instead of estimating a single co-integration relation in a single equation model, we will look at a multivariate setting where we jointly model several non-stationary time series and we can estimate several long-run relations. I will start with an introduction and the system approach to co-integration. Then we will use maximum likelihood estimation to estimate the parameters in our multivariate co-integration model. We also need a procedure to determine the co-integration rank, so how many co-integration relations we have. And I will end with a small empirical illustration on system co-integration analysis in R. All right, so last week we looked at single equation co-integration. While that was a good start on co-integration analysis, the single equation approach also had several drawbacks. First of all, we had to choose one variable among our non-stationary time series as the response, and all others were then treated as the predictors in our single equation framework. But of course, an obvious question is, which variable should we choose as the response? Unfortunately, the choice you make can also have an impact on the conclusion you draw, whether the series are co-integrated or not. And that asymmetry is, of course, not something that we want, since co-integration is a symmetric concept. Either the series are co-integrated in the long run, such that they move together, or they aren't. Secondly, we could only estimate a single co-integration relation. And that is a huge drawback, since we know that if we have k non-stationary time series, well, there can be up to k-1 co-integration relations. And of course, we would also like to estimate those. Related to that, the third drawback is that we were not able to figure out whether there were more than one co-integration relation. And so we could not know how many there were. So all this combined makes it clear that the single equation framework for co-integration is a nice starter, but we would like to tackle each of these drawbacks and take our co-integration analysis one step further. And that is exactly what we're going to do with the system approach to co-integration as put forward by Johansen. So let's have a closer look at this multivariate approach to co-integration. We will denote the n-dimensional vector of non-stationary time series by yt. And in this course, we will assume that each component in this vector is integrated of order 1. Johansen's co-integration framework then starts from the vector error correcting representation from last week. So the vector error correcting representation. How does this system of equation look like? Well, we write down a model for the series indifferences, where we regress it on its own lagged values, as we would normally do in a normal VAR. But we also add here the lagged values of the series in levels. And by doing that, we discussed last week that we correct the short-run dynamics towards the long-run equilibrium. Last week, we've seen that the presence of H co-integration relations implies that the matrix in front of the series in levels, so the Xi not over here, has reduced rank H such that you can decompose it in terms of two lower rank matrices. You might observe here that the notation is slightly different from what we've seen last week. The two are, of course, equivalent, so it's just a matter of rewriting, but we will work with this decomposition of Xi naught in terms of alpha and beta today, as this is most often used in Johansen's literature. Now, what did these low-rank matrices capture? Well, the matrix in front of the series in levels, so the beta prime over here, contains the co-integrating vector. vectors, so the coefficients of the time series in each of the H cointegration relations. And the matrix alpha contains the adjustment coefficients that measure the speed of adjustment of our series to the cointegration relations. Now, how will we estimate the parameters in our model? Subject to the restriction that there are H cointegration relations? Well, we will use maximum likelihood estimation, namely Gaussian maximum likelihood. So we will work with a normal distribution for our error terms. And today we will go over the derivations of the maximum likelihood estimator.